Vectors. Objectives. View vectors geometrically. Find magnitude and direction. Perform vector addition and scalar multiplication. Find the component form of a vector. Find the unit vector in the direction of vector v. Perform operations with vectors in terms of vector I and vector j. And find the dot product of two vectors. A geometric view of vectors. A vector is a specific quantity drawn as a line segment with an initial point where it begins and an arrowhead at the terminal point where it ends. A vector is defined by its magnitude, or the length of the line, and its direction, indicated by an arrowhead at the terminal point. Thus, a vector is a directed line segment. There are various ways of representing vectors. Lowercase boldface type with or without an arrow on top. Normally when we're handwriting vectors, it's hard to show that we are writing in bold, so we tend to write an arrow on top indicating in handwriting this is a vector. Given initial point P and terminal point Q, a vector can be represented as PQ with an arrow over the top, the blunt end over the beginning, and the arrow going last over the terminal point. With initial point 0, 0 and terminal point AB, a vector may be represented as angle parentheses AB. This vector in standard position is called the position vector. To change any vector into its position vector, we think about the change in the x and y coordinates. If the initial point of a vector CD is C with coordinate x1, y1, and the terminal point is D with point x2, y2, then vector AB will be found as x2 minus x1 and y2 minus y1. In the figure, we see the original vector CD and its position vector AB. Point C is the point 2, 2, and point D is the point 7, 4. So to find position vector AB, we take 7 minus 2 and 4 minus 2. So the position vector is going to be 5, 2. And you can see clearly that the vector has ended here in the position vector at the point 5, 2. So it's a nice way to reference vectors. Find the position vector given that vector v has an initial point at -3, 2 and a terminal point at 4, 5. Then graph both vectors in the same plane. So let's find the position vector AB. That will be 4 minus -3 and 5 minus 2. So vector AB, the position vector, will be 7 and 3. So we start with the position vector at the origin and we will terminate at 7, 3. Making sure to put an arrow there at the terminal point. Now let's go back and draw the original vector. It started at -3, 2 and ended at 4, 5. So when we draw these, we can see they are of the same length or magnitude and the same direction, given that they're both going up and to the right and they're at the same angle. We see that they're parallel. Finding magnitude and direction of a vector. Given a position vector v equals AB, the magnitude is found by the square root of a squared plus b squared. Geometrically, this can be viewed by using the Pythagorean theorem. Here we have the value of a, here is the value of b, and when I make a right triangle here, then that magnitude is represented by the length of that hypotenuse. So that's the reason that the Pythagorean theorem works here. The direction is the angle formed with the x-axis or with the y-axis, depending on the application. Now for a position vector, the direction is found by the tangent of theta equals b over a, or theta equals the inverse tangent of b over a. Two vectors, v and u, are considered equal if they have the same magnitude and the same direction, or if both vectors have the same position vector. Find the magnitude and direction of the vector with initial point p, -2, 3, and terminal point q, 5, 7. Draw the vector. First, let's go ahead and find the position vector so that we have our a and b values. So vector v will be 5 minus -2 and 7 minus 3, which results in the vector 7, 4. Now I need to find my magnitude. So my magnitude is the square root of 7 squared plus 4 squared. So the square root of 49 plus 16, which is the square root of 65. My theta is going to be the inverse tangent of my b over my a. So putting this into the calculator, we make sure that we're in degree mode, and then we'll find our inverse tangent of 4/7, and that gives us approximately 29.7 degrees. Now let's go ahead and draw the vector. The position vector goes from 0, 0 to 7, 4. And remember to draw the arrow there at your terminal point. Performing vector addition and scalar multiplication. We can perform operations on vectors. While it is convenient to think of the vector u as an arrow or directed line segment from the origin to the point x, y, vectors can be situated anywhere in the plane. The sum of two vectors u and v, or vector addition, produces a third vector u plus v, the resultant vector. To find u plus v, we first draw the vector u, and from the terminal end of u, we start to draw vector v. In other words, we have the initial point of v meet the terminal end of u. The sum u plus v is the resultant vector because it results from addition or subtraction of two vectors. The resultant vector travels directly from the beginning of u to the end of v in a straight path as shown. Here I have my vector u. I'm going to use that and redraw it here. And then where that terminates, I'll pick up and draw vector v. The same angle and same length as it is over here, just drawing it starting from the end of u. And wherever we stop, that is the terminal point for u plus v. The beginning point is where we started in all of this, at the beginning of u. So this here is our vector u plus v, the resultant vector. Vector subtraction is similar to vector addition. To find u minus v, view it as u plus the opposite of v. Adding negative v is reversing the direction of v and adding it to the end of u. The new vector begins at the start of u and stops at the end point of negative v. So we would pick up this vector u and move that here. At the end of u, we have vector v, except we're taking the opposite of it. So this is turned around in the opposite direction. The arrow is no longer there. So we'll pick up that vector and start at the end of vector u and travel in the same angle and the same length as vector v in its negative direction. My resultant vector begins at the beginning of u and ends where we left off with subtracting v. So the purple vector is the combination of u and negative v. Given vector u, 3, negative 2, and vector v, negative 1, 4, find two new vectors, u plus v and u minus v. So my vector u plus v, adding those vectors, will have 3 plus negative 1 and negative 2 plus 4. The resultant vector is 2, 2. With u minus v vectors, I have first the u, the x component, and subtracting the negative 1 makes that a plus 1. Then I have the vertical component here of negative 2, and I'm subtracting the other vertical component. This gives me the vector 4, negative 6. Scalar multiplication. In scalar multiplication, each component of the vector is multiplied by the scalar. Thus, to multiply vector v equals ab by k, we have kv equals ka kb. Only the magnitude changes, unless k is negative, and then the vector reverses its direction. Given u equals 3, negative 2, and v equals negative 1, 4, find a new vector w equals 3u plus 2v. So vector w will be 3 times vector u, that means 9, comma, negative 6, and we're adding 2 times the u vector. That will be negative 2, 8. Now when I add these, I'll have 7, 2 as my resultant vector. Finding component form. In some applications, it's helpful for us to be able to break a vector down into its horizontal and vertical components. For example, the position vector 3, 4 comes from adding the vectors v1, shown in red here, and v2, shown in blue. We have v1 with initial point 0, 0 and terminal point 3, 0. We also have vector 2 with initial point 0, 0 and terminal point 0, 4. Find the components of the vector v with initial point 3, 2 and terminal point 7, 4. Vector v, first we want to find the position vector. The position vector will be the terminal minus initial, terminal minus initial. So vector v results in 4, 2. If I were to graph this, then I could say that it is the result of adding vector 1, which is 4, 0, and vector 2, which is 0, 2. So horizontal and vertical components of vector v. Finding the unit vector in the direction of vector v. It's useful to find a vector in the same direction as the given vector, but of magnitude 1, called a unit vector. Unit vectors are defined in terms of components. The horizontal unit vector is written as I equals 1, 0 and is directed along the positive horizontal axis. The vertical unit vector is written as j equals 0, 1 and is directed along the positive vertical axis. The position vector AB is written as v equals AI plus bj. This vector sum is called a linear combination of vectors I and j. Any vector divided by its magnitude, which is a scalar, is a unit vector. So if v is a non-zero vector, then v over its magnitude is a unit vector in the direction of vector v. Find a unit vector in the same direction as v equals -5, 12. First, let's find the magnitude of vector v. It's the square root of -5 squared plus 12 squared, which is the square root of 169, which is 13. Now we take vector v and we divide it by the magnitude of vector v. So I'll have a -5/13 vector I plus 12/13 times vector j. This is the same as if we would write -5/13 12/13 in our angled parentheses. Given initial point p sub 1 equals -1, 3 and terminal point p sub 2 equals 2, 7, write the vector v in terms of I and j. So first we need to find the position vector. The position vector will be 2 minus -1 and 7 minus 3, and this gives us the vector 3, 4 as a position vector that started at the origin. So vector v can be written as 3i plus 4j, where my I and j are both the unit vectors. Find the sum of v sub 1 equals 2i minus 3j and v sub 2 equals 4i plus 5j. So vector v sub 1 plus vector v sub 2 is equal to 6i plus 2j, with I and j being unit vectors. Vector components in terms of magnitude and direction. Given a position vector v equals xy and a direction angle theta, the cosine of theta will be equal to x over the magnitude of the vector v. We can see this with right triangle trigonometry. If this is our vector v, and this is the angle theta, I know that this is the x, this is the y, and the hypotenuse is the magnitude of that vector, or the length of the vector. So the cosine of theta is adjacent over hypotenuse. So it's very clearly just right triangle trig. X is going to be equal to the magnitude of the vector times cosine of theta. The same goes for the sine of theta. The sine of theta is equal to y over the magnitude of v. Looking back at our triangle, the sine of theta is opposite over hypotenuse. So we have here that y is equal to the magnitude of the vector times the sine of theta. When we extend this understanding, we can see that vector v is equal to xi plus yj. That's the same as the magnitude of the vector times the cosine of theta I plus the magnitude of the vector times the sine of theta j. And magnitude is expressed as always as the square root of x squared plus y squared. Write a vector with length 7 at an angle of 135 degrees to the positive x-axis in terms of magnitude and direction. The first thing that we'll do is find the cosine of 135 degrees. The cosine of 135 degrees is the negative square root of 2 over 2. And the sine of 135 degrees is positive square root of 2 over 2. We've been given that the length is 7. This means the magnitude of vector v is 7. So now we have everything we need to put this together. Vector v is equal to 7 times negative square root of 2 over 2 times vector I plus 7 times positive square root of 2 over 2 times vector j. This is going to be equal to negative 7 square roots of 2 over 2i plus 7 square roots of 2 over 2j. A vector travels from the origin to the point 3, 5. Write the vector in terms of magnitude and direction. So the first thing, we need to recognize that this is vector v, the position vector, because it's traveled from the origin to the point 3, 5. So we can find the magnitude of vector v. That's going to be the square root of 3 squared plus 5 squared. That's the square root of 9 plus 25, which is the square root of 34. Now I know that my cosine of theta is x over the magnitude of the vector. X is 3. The magnitude of the vector is square root 34. So I'll use my calculator to figure this. Making sure that the calculator is in degree mode, we'll go into the trig menu and find the inverse cosine function. That's the inverse cosine of 3 over the square root of 34. And make sure that you get out of the square root there and then close your parentheses. We've got theta is approximately 59.04 degrees. So So this means my vector v is equal to the square root of 34 times the cosine of 59.04 degrees I plus the square root of 34 times the sine of 59.04 degrees j. Finding the dot product of two vectors. The dot product of two vectors v equals ab and u equals cd is the sum of the product of the horizontal components and the product of the vertical components. To find the angle between the two vectors, we use the formula below. Cosine theta equals v over the magnitude of v times u over the magnitude of u. So finding the dot product of v and u here, I know I have v dot u vectors. That's going to equal the horizontal components multiplied together plus the vertical components multiplied together. So this is a negative 15 plus 48, which is 33. So the dot product of two vectors is just a scalar. Now let's find the angle between vectors u and v. The first thing that we'll do is find the magnitude of those two vectors. The magnitude of u is going to be the square root of negative 3 squared plus 4 squared, which is 5. And the magnitude of vector v is going to be equal to the square root of 5 squared plus 12 squared, which is 13. Now we move to our formula. Cosine theta is equal to negative 3i plus 4j over 5 times 5i plus 12j over 13. So the cosine of theta is equal to negative 3/5 times 5/13 plus 4/5 times 12/13. So the cosine of theta is equal to negative 3/13 plus 48 over 65. So the cosine of theta is 33 over 65, and I can use my calculator to figure the angle. Making sure that we're in degree mode, we'll go to the inverse cosine and enter 33 over 65. And we get about 59.5. So theta is about 59.5 degrees. The angle between vectors u and v is 59.5 degrees.